So dear students, now let me start with the third property of Jacobian. In the last class we have discussed two important properties of Jacobian. Now let me discuss about another more important property of Jacobian. Okay, and what this property is? This is actually the property we will see when the Jacobian will vanish. Okay, so when the Jacobian will be vanish, suppose that u is the function of x and y. Suppose u is the function of x and y, and also v is the function of x and y. Now here u is the function of x and y, where x and y are the independent variable, and also v is also the function of x and y. Now the question is that, is there any functional relationship between u and v? Is there any functional relationship between u and v? If there is a functional relationship between u and v, that is, if u can be written in terms of v or v can be written in terms of u, in that case the Jacobian, that is del uv by del xy will be 0, and that will be 0. Okay, so this is actually the property. Or if you take this as a function of xyz, u as xyz and v as xy, if you take that u is the function of xyz and v is the function of xyz, and also another one function, that is w is also the function of xyz, then obviously if there is a functional relationship between u, v and w, then obviously we will get a Jacobian j u v w xyz, or you can write it as symbolically like del u v w and del xyz. Let me correct one thing. Actually in the last class, in the previous class, I have used j here also. Okay, so please correct this will be del. Okay, I have written there j. Okay, so there is silly mistake, so you can, though this is a matter of notation, it does not matter, but it is better to write in actual notation. Okay, conventional notation. So you can check and correct this as a del, okay, instead of j. So this will also be vanish. So this is actually the property when the Jacobian vanish. If there is a functional relationship between u and v, then the Jacobian will vanish. Let me take one or two examples so that the thing will be clear to you. Okay, so let me take an example. So here given that u is equal to xy plus yz plus zx, xy plus yz plus zx, and v is given as equal to x square plus y square plus z square, x square plus y square plus z square, and w is given by x plus y plus z, x plus y plus z. Now what you have to do, you will determine whether there is a functional relationship or not. Okay, so let me write down the complete question. So determine whether there is a functional relationship, between uv and w. So what you have to do, you have to first check the Jacobian. Okay, so first you have to check the Jacobian. If the Jacobian is 0, then you can easily say that there is a functional relationship. So what will be the Jacobian? Jacobian is here del u v w upon del xyz, and that will be, you know the definition, that is del u del x, del u del y, and del u del z, where by del v del x, del v del y, and del v del z. Similarly, del w del x, del w del y, and del w del z. Okay, so you have to substitute. So what is del u by del x? You can get from this. So del u by del x is y plus z. So it will be y plus z. The next del u by del y, you will get y plus z, then you will get z plus x, then you will get x plus y. So please check. Okay, then what will be del v del x del y? It will be 2x 2y and 2z. Just partial differentiation, nothing else. And the last one is 1 1 1. Okay, now if you expand this determinant, then you will get, if you solve it, you will get 0. Okay, then you can easily say that there is a functional relationship between these two. And now, what is the relation? You can find the relation from here easily. Okay, so what is the relation? Here w is given and v is given and u. So if you take square of w, the w is given. What is w? W is here x plus y plus z, and if you take square of it, then w square will be this. So it will be x square plus y square plus z square plus 2 into xy plus yz plus zx. Now you can see this is your v square, v actually, plus 2 into this is u. So w square is nothing but v plus 2u. So there is a functional relationship between u, v and w. And from where you can understand from this Jacobian. If Jacobian is 0, then obviously there will be a functional relationship between them. Okay, now let me move to the next question. Let me give you one more example. Okay, so here given that u is equal to x plus y divided by 1 minus xy, and v is given as again tan inverse x plus tan inverse y plus tan inverse y. So what you have to choose? You have to check again if there is any functional relationship or not. So what you have to do? You have to again take the Jacobian, that is del uv and del xy. And again from definition we know that it will be del u del x, del u del y, and del v del x and del v del y. So you have to take a differentiation of this. So you will get what? If you take differentiation of this del u upon del x, so you will get just it will be just, let me put here, definitely we have to do differentiating. Okay, I am giving you the result only. And this is very easy, the partial differentiation only. Then you will get del u by del y from here, that you can see, that is 1 plus x square divided by 1 minus xy whole square. Similarly, if you get if you do del v by del x, you will get 1 by 1 plus x square and 1 by 1 plus y square. Okay, and if you solve it, you will get again 0. So obviously there is a relationship between these two, and you can see from here the relationship. Again you can see the relationship here. U and v are given. Okay, and v is equal to what? Tan inverse x plus tan inverse y. And you know, I think, the formula, that is tan inverse x plus tan inverse y is equal to nothing but tan inverse x plus y divided by 1 minus xy. So if this tan inverse x plus tan inverse is v, so v is nothing but tan inverse u, or you can say u is equal to tan v. So this is the relation. So here the functions are so easy actually, so that you can understand that these are the known functions, so that you can understand that there is a functional relationship directly. But when the functions are so complicated, you cannot say only by seeing the function. So if there is a relation, then you have to check the Jacobian. If the Jacobian is 0, then definitely there will be a relation. If the Jacobian is not 0, then obviously there is no any relation between u and v. Okay, So this is how we can solve this kinds of problem. Now let me give you another important thing, that is Jacobian for implicit function. Okay, so next topic is Jacobian for implicit function. So let me discuss about Jacobian of implicit function. Implicit function. So what this actually mean? We know about implicit function. Let me take two implicit function, okay, such that f1 is function of x, y and u v is equal to 0, and f2 also x, y, u v is equal to 0. So here x, y are the implicit functions of u v. Okay, so x, y are the implicit function of u v. Now what you have to do, you have to remember a property. Okay, a very important property. I am not going to derive this property, just use this property. Okay, just use this property. In this situation, if there is a function like this, f1 xy uv and f2 xy uv, then you will get a relation, that is del uv upon del xy. That will be, this is the relation is just like differentiation of implicit function. Okay, just like differentiation, instead of differentiation, here is the Jacobian. Okay, so del uv del xy is nothing but minus 1 whole square into del f1 f2 divided by del xy comma del whole divided by del f1 f2 del uv. This is the function like this. When we have function f1 of x comma y is equal to 0, we have studied this thing in differentiation. You can remember, by analogy you can remember this result like this, and f2 xy is equal to 0, and if you want to know about the dy by dx, then what we have minus del f1 del x divided by del f1 del y by del y. We have studied this thing. There is a differentiation of implicit function, and here the relation is like this. Instead of derivative, here is the Jacobian, del u del v del of uv del of xy. So f1 f2 xy, f1 f2 uv. Now let me solve a problem so that you can understand. You have to use this property. Okay, you don't need to prove this thing. You have to use this. Just there is a derivation also, but you don't need to do this here. Okay, so let me give one example so that you can understand everything. Okay, so here we have a very good example. Okay, that if x square plus y square minus plus u square minus v square is equal to 0, and uv plus xy is equal to 0, then prove that what del uv del xy is equal to x square minus y square divided by u square plus v square. Okay, so we have two functions. Can you see? One is this, another is this. So f1, you can say f1 is this, that is x square plus y square plus u square minus v square, and f2 is this, that is uv plus xy, that is uv plus xy. Now you have to calculate two Jacobian. One is del, you can see from the previous page, this del f1 f2 xy, del f1 f2 uv. Okay, if you want to calculate this, so what you have to do, you will just del f1 f2 del xy, you have to calculate this, and you have to calculate del f1 f2 del uv, del uv. So what will be this? Let me calculate. Okay, so what will be del f1 del f2, del f1 f2 x1 xy, del f1 del x, del f1 del y, del f2 del x, and del f2 del y. Similarly, you will get from here, you will get del f1 del u, del f1 del v, and del f2 del u, and del f2 del v. Okay, now if you calculate, what you will get, please calculate this thing. Again, you have to calculate this thing. So what is del f1 del x is 2x, del f1 del y is 2y. So it will be what? It will be 2x 2y. And what is del f2 del x? Del f2 del x you will get from here. Del f2 del x is y, and del f2 del y is x. So 2x 2y and yx. So you will get from here 2 into y square minus x square minus y square. Okay, similarly, if you put here, what is del f1 del u is 2u, del f1 del v is minus 2v, then del f2 del u is v, and del f2 del v is u. So you will get 2 into u square plus v square. You will get what? 2 into u square plus v square. Okay, so now you have to calculate this. So what will be del uv del xy? So it will be obviously minus 1 whole square, minus 1 whole square. Okay, so it will be minus 1 whole square into, what is happening, del f1, this divided by this, this divided by this. So what is this? This is 2 into x square minus y square divided by 2 into u square plus v square. So you will finally get x square minus u square plus v square. So this is the required result. This is the required result. So this is how you can use the properties of Jacobian. Okay, so these are the important properties of Jacobian. Now let us see the application of this Jacobian when we transfer the area element or the volume element from one coordinate system to another coordinate system. Okay, so let me see that case also. Okay, so the application of Jacobian, and this is a very important application. We will apply this several times. Okay, so let me see that application of Jacobian for transformation of area and volume element from one coordinate system to other. Okay, from one coordinate system to other. So let me see. So let me first take from Cartesian to polar, and this is obviously two dimensional, the case of two dimensional. This will be used many times in double integration and triple integration. Okay, so what is the area element in Cartesian? That is dA is nothing but dx dy. okay, in xy plane. Now when we take the transformation relation, that is x is equal to r cos theta and y is equal to r sin theta, then on plane polar coordinate we have the area element is dr d theta multiplied by the modulus of Jacobian. And what is the Jacobian here? Here the Jacobian will be obviously xy r theta, and that is del x del r and del x del theta, del y del r and del y del theta. And I have calculated previously that this will be r. So just simply differentiate and if you put, you will get. So in that case, this dA will be r into dr dA. So this is how you can transfer the area element from Cartesian coordinate system to circular polar coordinate system. Okay. So now if you want to change the volume element in cylindrical polar and in spherical polar. Okay. So now change of volume element. Okay. Change of volume element. Now in cylindrical coordinate. Okay. Now in cylindrical coordinate, what is the relation? This means x is equal to rho cos phi, y is equal to rho sin phi, and z is equal to z. But the point on cylindrical coordinate, that is in the coordinate system, there is a cylinder like this. Okay, so this is our z axis, this is our x axis, this is a y axis, this is x, this is y, and rho is the distance from the axis to the point on the surface P, and this point is nothing but rho, phi and z. Okay, so this is the rho and the vertical distance is z, and this is the angle phi. This angle is phi actually. This angle is phi. This angle is phi. Okay, so this is rho phi z and the relation is like this. Okay, so now what will happen? The volume element in Cartesian coordinate system is nothing but dx, dy and dz. Okay, so this is in Cartesian coordinate, but this is will be in polar coordinate. In cylindrical polar will be mod j into dr. So we have d rho, d phi and dz. And if you calculate the mod j here, we will again get only r. So if you take mod j will be here x y z divided by rho phi z, obviously. So if you calculate this thing, you will get again r. So it will be rho here, not r actually, rho. I have taken rho here, so you will get rho d rho d phi dz. Similarly, in spherical polar coordinate system, and this relation, if you don't know this relation, I will tell you when I will teach coordinate system. There will be a separate class for coordinate system in classical mechanics. When I will discuss classical mechanics, I will tell you how these will be changes, how these changes are written. Okay, in vector calculus, in vector algebra, or in classical mechanics, I will tell you. Okay, I will tell you this thing. So don't worry. If you don't know how these relations are written, don't worry. I will tell you. Okay, but if you know, then it is very easy, you know. So I will tell you. So don't worry. But now it is just I want to see that what are the relations actually. Okay, what are the relations? And these are very easy. Okay, so here our goal is to apply Jacobian. Okay, how by using Jacobian you can transfer the volume element from one coordinate system to another coordinate system, area element from one coordinate system to another coordinate system. Similarly, let me find for spherical coordinate system. In spherical coordinate system, what will happen? the transformation relations will be, let me first give you the transformation relation, that will be x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. And here if you take, this is x axis, this is y axis, and this is z axis, then here is a point P which is r theta and phi. Okay, so this is r, this is theta, and if you take the projection of this on xy plane, then this will be phi. Okay, so don't worry. So these are the notation, and how these are coming like this I will tell you. If you know, then it is okay, but if you don't know, so don't worry, I will tell you. Okay, now here again the volume element in Cartesian coordinate is very simple, that is dx dy dz. And if you talk about in spherical polar, then you have to calculate mod j and into dr d theta d phi. Now what will be mod j? Mod j, so j here xyz and r theta phi. So again you have to calculate this determinant, and you will get the determinant with nothing but r square sin theta. So you have to put here. So this is homework for you. Okay, so please calculate this Jacobian. Please calculate this Jacobian. So it will be r square sin theta dr d theta d phi. So this is in spherical coordinate system. Okay, so this is how the Jacobian can be applied, and you can easily find the transformation relation of area element, volume element. But this can also be proved by using the geometry. Okay, but here our goal is to show you the application of Jacobian. Okay, so by using Jacobian, how you can transfer the relations, transfer the element, area element or volume element from Cartesian to polar, I have shown you. Okay, so these are some applications, and there is also one or two things I think. If you want to know the area element, okay, if you want to know the area element in cylindrical coordinate, so that can you also take. So the area element in cylindrical coordinate, also if you talk about the area element, so let me give you, the results will be useful. Okay, so if you want to calculate the area element, so dA will be obviously just, here will be d phi and dz only. Okay, so that will be d phi and dz mod j, and mod j what, r or rho you can say, so rho d phi dz. Okay, so this will be the area element in polar, in cylindrical coordinate. Okay, similarly if you want to know the area element, so mod j is, you know. Similarly if you want to area element in spherical coordinate, you will also get, okay, you will also get the area element here. Area element will be dA, and that will also be mod z into d theta d phi. Okay, so only two variables are there for area element, where in volume element there are three, r theta phi, here only theta phi. Okay, r is just the distance and area is here. Okay, here. So the variable is only theta and phi when we will talk about area, and this j is what, j is again r square sin theta, so it will be d theta d phi. Okay, so just remember this result. Okay, just remember this is the application of j actually. So we have just here we want to calculate this j, but how these are happening, how these two are variables, etc., etc., why these relations are coming, I will tell you when I will teach you this chapter, that is a coordinate system. Then I will tell you how these are coming geometrically. But now you don't need to think about geometrically, you just think about j, how you can transfer the area element by using j. Okay, and when that is area element, then only two variables are there, that is theta phi, or sometimes phi z, or sometime r theta. But when it is volume element, then all the three variables will be used, r theta phi or rho phi z, etc. Okay, and just multiply by mod j. When you will talk about this on polar coordinate, then just multiply by mod j. Okay, and if you calculate mod j, you will get this result. Okay, so this is how we can understand the Jacobian, and this is the complete course on Jacobian. So Jacobian is now completed. Now from the next class I will start the double integration and triple integration. Okay, after finishing the double and triple integration, this chapter of mathematical physics will be completed. That is single and multivariable calculus. Okay, so first chapter of mathematical physics will be completed after finishing the double and triple integration. So 2 or 3 class will be needed. Okay, so by using 2 or 3 class I will finish this section. Then I will move to Fourier series, differential equations. Okay, thank you.